Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We will begin. Okay, those are the magic words for our remote viewers. Hello, good afternoon, and welcome. I'm Mark Smith from the Microsoft Research Community Technologies Group. I am delighted to welcome here today Professor Michael Macy, Chair of the Department of Sociology at Cornell University. Dr. Macy's work of late has brought many of the core concerns of social sciences, in particular collective action dilemma theory, into the 21st century in his work on analyzing the archives left behind by, the many, many users of the Internet. He comes to us today to talk about a very exciting project recently funded by the NSF, in which the archive generated by Brewster Kahl's project, the Internet Archive, is being moved, or at least copied, to Cornell University, where it will then be subject to actual analysis rather than simple retention. Not knocking retention, it was quite an accomplishment, but analysis is certainly the next order of business. So I hope you will welcome with me Dr. Macy to hear more about that. So thank you, Dr. Macy.
Thank you, Mark. Is my microphone doing its thing for the inside and outside worlds? Okay. So, so I apologize for the change in name, but we started out with CyberTools, which was the name that NSF gave the project. And CyberTools Incorporated said, that name is taken. And so then Mark that afternoon said, well, I need to have the title for your talk, so I came up with Yesternet, but we decided that was a little too cute. And so the project is now called WebLab, or Cornell WebLab, and I'm going to talk about what we're doing and why. And to begin, so it may very well be that the era that we're entering will come to be known as the age of networks. We'll see. We'll have to stay tuned for another 10 to 100 years. But why might one think that this will be the age of networks? For one thing, there are fundamental changes in society that are associated with the emergence of with an information economy in which we have social life mediated by computers and social life increasingly being organized from the bottom up through processes that are peer-driven. We see this in news groups, in weblogs, the development of open source software, open source encyclopedias, reputation systems like at eBay that are self-policing, and self-organizing status hierarchies. But even perhaps more importantly for me is that we're seeing changes in social science, not just in society. And these changes, I think, are of extraordinary significance that is easily overlooked. For the past 100 years, we've been collecting enormous amounts of data about individuals, mainly through surveys. And we can then aggregate these data so that we know things about groups and populations. But what we don't know very much about at all is the very stuff of social life, which is social interactions. We don't know a whole lot about the structures of these networks, especially when they get large. We have networks that are small groups, but not for big populations. We know even less about how these networks change over time, and less still about the content of the ties, what goes on in the ties, processes like influence, imitation, or exchange. And the challenge is to get beyond data about the nodes, as it were, to understand the ties and the structures. But it is a challenge, and one reason it's a challenge is that we can't observe friendships. We can ask people about their friends, but we cannot interview a friendship. And these relations between individuals are difficult to observe. You have to be there when it's happening. Then they disappear. They're tedious to record. There's lots of data. The hand coding is laborious and time intensive. It's just a lot easier to administer a survey. And what happens then is that social science is shaped by the correlation matrix. I mean, that's basically what's driving most of the data analytic methods. It's some kind of covariance structure in which we have data on the attributes of individuals, and then we look at the correlations, and that's social science. We see these limitations even in areas like diffusion research, which is very much relationally structured. Diffusion studies tend to be very small scale. We're usually talking dozens or hundreds of adopters, rarely more, usually in a concentrated geographic space, and mostly about successes. Why? Because that's the stuff that gets recorded. So we don't know very much about the failures. We don't know much about the early stages before people started paying attention. We don't know much about the downside when the successes nosedive. We don't know much about the ways in which diffusions involve branching and the development of first and second cousins of an innovation. And finally, we don't have comparative studies of diffusions, either comparative across cultures or even just across the innovations themselves. And so we know surprisingly little. But the good news is that all this is changing. And the reason that it's changing is what brings me today to Redmond. And that is that increasingly social life is mediated by machines, by computers, such that social interactions leave a digital trace. And you find these traces on web pages and emails, in discussion threads, in the edits of wikis. And now we have the opportunity for automatic data collection without any human eyeballs involved. It's automatic data collection on millions of nodes of a network at multiple time points. And we have, meanwhile, the computational power to sort and analyze these massively large data collections, and even to visualize it. So this is really an extraordinary moment in the history of social science, when for the first time we're actually in a position to study social life, not individuals, but social life. And that's a fundamental change. It's something that really has not been done on a social scale. And this means that we can focus on social relations, the ties of the network, not just the node. We can look at the processes that go on inside the ties. We can look at deference, at imitation, at influence. We can look at changes in the structures of ties, processes like clustering. We can study how social life emerges from the bottom up. Instead of focusing on formal institutional structures and top-down hierarchical processes, we can look at things like socially reinforcing dynamics, sometimes called the Matthew effect, the adage, the rich get richer. And one of the ways that we can do this, to find these digital traces of social interaction, comes to us thanks to Brewster Kahle, who 10 years ago, or thereabouts, decided to take his winnings from the NASDAQ lottery and to record for posterity the Internet, something which I think many, many years down the road people will look back and see was a remarkable contribution to the human race. And what he did was to set up a mechanism for the archiving of web crawls taken about every 2 months over the last 10 years. And we're up to about 600 terabytes altogether. It's increasing at about a terabyte per day now. Of course, it will be increasing even faster than that shortly. The metadata for the archive has formatting information, the links, the anchor text, the file types, and these data are organized in a way to provide people with historical access to a particular website, as Mark noted. So here's what the Wayback Machine looks like. The Wayback Machine is the interface for the Internet Archive, and for those of you who have not been there, this is what you see when you go to the Wayback Machine. And here I'm searching on Cornell.edu, and I have now the nearly 10-year record of the Cornell.edu website. And here's the earliest Cornell web page from June 5th, 1997. Not too impressive. Here's their web page last month. You can see the changes that have occurred. Those involve innovations, which can then be studied. Anybody remember this one? This is the earliest Microsoft.com website at the Wayback Machine. No doubt everyone here has visited this many times to pay homage. And here's the web page on April 1, 2005. And I put that up just to point out that the Internet Archive is always 1 year lagged, so the most recent pages are now May of 2005. Here's the earliest Microsoft Research web page from October of 96. And there's the bottom of the page. And here's the MSR web page from April of 2005. Also, it's come a long way. So that's the Wayback Machine, but what we're building is something that we think of as a machine for going the way to chart the way forward. The Wayback Machine allows us to track a particular URL, and indeed we are actually writing scripts to track, let's say, about maybe 500 URLs, and that's about the limit of what you could do with the Wayback Machine. And it's not designed for relational analysis, for understanding links among pages. It's really for looking at the trajectory of a page. But imagine that the Internet Archive was accessible as a database for relational analysis. This would indeed be unprecedented as an opportunity for doing research on social and information networks in ways that are really breathtaking to think about. And that is indeed what we are hoping to do in the next months and years at Cornell with the web, where we will have petabytes of online data from web pages. And there are other online data sets that are becoming available that are also extraordinarily large, although tiny in comparison to the Internet Archive. So here at MSR, there's NetScan data. Cornell has the arXiv data set of citations. Increasingly, we're seeing these sensor-equipped PDAs and smartphones that are collecting data on physical interactions among people. There's a project at Intel Research and at University of Washington working on this. Is a project that my colleague at Cornell, Jerry Gay, is doing. There may be projects here at Microsoft Research. And then yet another development, social scientists setting up their own websites to run experiments online. So one of the very first to be published in Science about a month ago, developed at Columbia University by Matt Salganic, a former Cornell sociology graduate student, now working with Duncan Watts. And they set up a music download site and then ran experiments to study the decisions that people make about music downloads. At Cornell, we're developing a gaming website where we're going to have a game for people to play. I met yesterday with people at Cornell doing research on family and made a pitch for them to write a big grant to NSF to set up a website for online dating, and would be free, and it would be advertised as we're doing this for science, and oh, by the way, we will also use the science to help you find your perfect mate, but this is also a scientific project. And the data would then be used to have really unprecedented access to knowledge about the mating process among humans in a way that social scientists have never been able to do before. So these are all developments that signal a sea change in the way that social science is being done. And indeed, one could argue that doing social science in a way for the first time, because it's the science of social interaction, not just about individuals, and not just aggregations of individuals up to larger groups, but studying social interaction, the very foundation of social life. But the problem is that this is a little overwhelming. We've gone from having scant data and too little data in a way now to too much with web-scale data. And the problem is, how do you work with it? The technical challenges here are daunting indeed. And the old methods that we've used for data storage, data management, and data analysis just won't work. Entirely new tools are going to need to be developed for working with these data. One can't do manual coding when you're working with data at the web scale. So being able to process the data in ways that give you reliability this is a remarkable challenge. And finally, just privacy issues. The opportunities now with these data to triangulate on individuals in order to be able to potentially identify who they are, even to get it down to 1 in 1,000 or 1 in 10,000 raises real concerns about privacy. So there are new challenges that are unfolding before us that still need to be worked out. And in the face of these challenges, the response that I see developing is an alliance and a merger and collaborations between social, computer, and information scientists to bring together experts in natural language processing, in machine learning, in privacy, data mining, graph theorists, people who have knowledge in databases, coming together with people with expertise in network theory, in decision theory, game theory, social psychology, organizational ecology, people studying diffusion, people studying opinion dynamics, formal modelers, agent modelers. These, I think, are the important fields within social and information science that are likely to have very fruitful collaborations in tackling some of these challenges and opening up the opportunities to do analysis at the relational level. So at Cornell, we've actually done this. We put together a grant to NSF last year that involved these collaboration between social, computer, and information scientists. So we have Bill Arms, Jerry Gay, Dan Huttenlocker, John Kleinberg, all from computer and information science, myself and David Strang from the sociology department. And we have a large group of postdocs and graduate students, including people from Microsoft Research, Ted Welser and Tom Lento. And what we're doing is to convert the Internet Archive from an archive into a very flexible working database. So this involves copying the Internet Archive, transferring it to Cornell, and the plan is to get about 1/3 of the archive, about 200 terabytes, by the end of next year. And the transfer itself is going fine. That's actually pretty trivial. The tough part is what to do with it once it gets to Cornell, where the plan is for the data to be stored in a relational format that would be very flexible and would allow users to specify search criteria to pull out the data that they want to analyze in the format that they need. And as a sort of second generation of these tools, we're already beginning to do the groundwork to have NLP tools, and machine learning tools that will allow us to read the web pages, to train the algorithms to be able to pick up not just keywords, but to be able to do things like detect positions on issues and be able to identify where an issue is being debated, the sides that are being taken, who's for, who's against. There are some major limitations of these data. For one thing, the crawls are incomplete. In part, they're always incomplete just by the nature of how a crawl works, but also there are a lot of blocked sites. Then there's the sampling problem of whether or not this is indeed a representative sample of any meaningful underlying population. It's not just the issue of the digital divide, but even if that were not the issue of the demographic biases, it's just not clear what it is sampling. We have very little demographic data, very little geospatial data. And then finally, there's just the interpretation of what do these data represent? What's the interpretation of a hyperlink? Yes?
When you say they're blocked sites, do you mean those people requested to be blocked?
Both. So there are sites that are protected by robots.txt filters, and in addition to that, there are sites that are not protected before the fact, but the owners of the sites have asked after the fact to not have access to those sites, especially, for instance, if they took down their page and they want to be able to say, all right, I took down that page, therefore it is down, and it's down from history. And those pages have to then be preserved. You can't delete them, but they then have to be flagged so that people can't see them. So there's two ways that they get removed.
Do you have a sense of what percent of people going into block, how that might change once studies start to come out?
Well, it certainly, I mean, one would hope that it will change, and it changes on the fly. So, for example, newspapers are, I think, entirely or almost entirely blocked. So you can't get the New York Times with the Wayback machine. However, during the presidential election, an 8-month period before and then just after the presidential election of 2000, the Library of Congress had a massive series of crawls, daily crawls, actually hourly crawls over an 8-month period of a limited number of election-oriented sites, and they included newspapers. So the newspapers agreed to remove the restriction for that set of crawls. So it's selective. And arrangements can be made to have those things taken off, which is a hopeful sign. And that presidential collection, by the way, is an extraordinarily rich set of crawls because the temporal granularity is relatively fine, even though it's a smaller number of sites. Yes?
Are the hyperlinks marked so that you know when the first appearance and when the link to which it links change?
Well, it's, what we have, well, there are timestamps, and that's what we have, are the timestamps, and then one would have to construct the sequencing after the fact once one has the record of the timestamps. But this is, in fact, one of the issues that I wanted to speak to next, which is what is a link, and what do these hyperlinks represent? And in particular, what does it mean if a web page on a certain date has a link to another page, and then that link is removed, they decide to take it down. Then if you do a web graph, should the link be there or not be there? And how do you represent that? Well, it's sort of there because it was there, but then they took it down, so it's not there now. So there are some very tricky issues about the fact that these links are here today and gone tomorrow, and they appear and they disappear. It's not a stable phenomenon. This is not a highway system. It's not even as stable a structure as airline routings, which are also a moving target. This thing is really in flux. But the hyperlinks are really only the surface of the web. It's not the only link. The links are indeed interesting. They do have an interpretation. At the most literal sense, the links show exposure. So presumably somebody has seen the other page. They know about its existence. And that's useful information if you're trying to study the spread of a social contagion. You need to see who was exposed to it. And Kleinberg argues that they can be interpreted as indicating deference, status, the authority, the credibility of a source. So they can have that social interpretation. And others have suggested that they indicate trust, that you believe the content of a page if you tell people to go there or help them find it by providing a link. So there is social meaning to these links, however ephemeral they may be. But they're not the only links. And one can, I think of the web as having a graph structure that's given by not just the hyperlinks, but by other kinds of ties. And in particular, that we can decompose the web into interlock and affiliation networks. So if we start with just in general terms, if we think of the web as a bipartite graph, which is just simply a list, it's simply a list of the members of groups, we can decompose that set of lists. One way we can decompose it as an interlock network consisting of groups that have common members. So at the top here, what we have just the groups. So we've taken just this part of the bipartite graph, and we now have the structure of the groups where the ties consist of common members. And we can parse it the other way, and now we have an affiliation network of the members who are tied together by their presence at the same event or their membership at the same time in a given group or organization. And we can do the same thing with the web. So we can decompose the web into interlock and affiliation networks. And we do this by taking the page content and doing the same thing that we do with offline networks. We can develop the interlock network by understanding people as simply the links between sites. And we can do things like study the movement of people across organizations, discussion groups, communities, even just topics. So we can see how you can have a network of topics connected by the people who write about them. And we can also decompose it as an affiliation network in which individuals have some connection to one another by virtue of common participation or membership in an event or in a group or community. And one of the most exciting areas for immediate use of these data is for the study of innovation and for the spread, the evolution, the mutation of innovation in ways that are really unprecedented. And we can start with just the most basic question that motivates pretty much all research on the diffusion of innovation, which is to ask, what is the probability that somebody will adopt this innovation given that some of their friends and neighbors have adopted? And how does that probability change with the number of their neighbors who have adopted and the structure of ties among those neighbors? And we can apply this. We should really think of innovation here in very broad terms, not just as the latest gadget, and not just even as new technology, but it can be a social movement, it can be a new word, it can be a rumor, an urban legend, it could be an online community. There are all kinds of things out there that spread virus-like through social life, leaving a digital trace on the web, which we then pick up. And this allows us to study innovation in ways that we never could do it before. So a perennial problem in the study of innovation is that you can't find the dogs that don't bark. And with traditional methods of data collection, that's all you know. You know about the barking dogs because somebody heard them and wrote it down. You don't know about the ones that nobody noticed. And that's going to allow people It's going to allow scholars to study innovations that were nipped in the bud, so to speak. I guess I'm mixing my metaphors here. Nipped in the bud by dogs that don't bark. But we'll be able to study the ones that just started to go and then don't make it. And why does that happen? And that's going to, I think, expose mammoth amounts of confirmation bias in previous studies, where it's going to turn out that a lot of the properties of the ones that succeed, we're going to find them also in the ones that failed. We just never knew it because we couldn't study the ones that didn't fail, that failed. We'll also be able to look at the downward trajectory. And it may turn out that the dynamics of the downward spiral are very different from the upward. It's not just a reversal. And we'll be able to go back to the early takeoff period and learn things even about the ones that succeeded. So even for the successful innovations, which we know a fair amount about, we don't know much even for those about the early days before it came to the attention of the people who then recorded all the data. Now we'll be able to do that, go back and look at those early trajectories and find out how did they get critical mass, how did they take off. And that's going to really change lots of stuff. It's going to change the way we understand social evolutionary processes. It's going to change the social epidemiology of contagions. It's going to change market research because we're going to have a much richer understanding of how stuff jumps from person to person and from adopter to adopter, and also how it doesn't. We'll also be able to look at units different just from individuals, but also units at a higher level of aggregation, diffusion across organizations. And indeed, there's some big advantages to using organizations as the units, because for organizations, we can have a lot more data about context. We can know who they are. So if we're looking at hotels or universities, we can identify who they are and know something about them, and then do the same type of analysis of the spread of these innovations across those units. So we'll be able to do things like look at downsizings. We'll be able to look at the movement of managers and personnel across organizations. We'll be able to see what happens when people move from one organization to another. To what extent do they take ideas with them that then change the unit that they then move to, or to what extent do they get changed by that process? One study that already has been done by a group at Cornell looked at 875 live journal communities, focusing on individuals who were 1 degree removed from those communities. That is to say, these were individuals who had at least one friend in the community, but were not in the community themselves. And then asks, what's the probability that that individual will then join that community at some point in the future as a function of the number of their ties into the community and the structure of relations among those network neighbors. Now, if you look at the standard models in the diffusion literature, the standard model is a sigmoid, an S-shaped curve, where the threshold phenomena, the threshold effect is such that it's a ramp up slowly, then you hit a critical point, and then you reach saturation where it's increasing redundancy. But in fact, what the Kleinberg's group found is a little different. So here we have a pictorial representation. So individual A has just one tie into the community. B has 3 ties, but the neighbors are not tied. And then C has 3 ties, but there are also ties among the neighbors. That is to say, we can count not just the number of neighbors, but the number of triads, the number of triangles. And we can ask, how did the number of neighbors and the number of triads shape the probability that the individual will join? And what we find is that as the number of ties goes up, and especially as the number of triads goes up, so too does the probability of joining. So instead of getting the characteristic S-curve, actually the function is pretty much concave, such that a few friends will pull you in, and then beyond that, it becomes increasingly redundant. We also find, interestingly enough, yes?
Can you go back a slide?
Yeah. Yeah, right. That's right.
Is like
Sure.
5, right?
That's right. That's right. Yes, of course. So if you magnify if you stretch it out from 0 to 3 friends, you get that little bit of flatness. So you have to get 1 to get the thing going. But in the larger scheme of things, step back from it even a short distance, and it's pretty much concave. That is, the expectation would have been that the shape would go more like, at least like that, and then up. And what this is suggesting is a very low threshold for joining, a very low threshold for joining.
A very low threshold with the total cumulative probability of 2%.
Yeah, that's right.
So there's a so the difference between someone who joins and doesn't join is they have more than 3 friends, at which point they've got a 2% probability of joining.
Right.
2% greater than whatever the decimal. Because of people who don't have friends also.
That's right. That's right. So this is picking up the marginal impact of each additional friend.
Is that marginal difference or is that actual difference?
Well, people who have no friends will also have some positive probability of joining.
Right.
It's not 0.
Yes, but so this isn't above the
So
0.
we don't know what that is.
Right.
So it's scale. Now, what's more interesting, I think, than the number of friends is the effect of the number of triads. And this has 2 really interesting and important interpretations. So different network theories would suggest different points of view on this. The theory of weak ties and also the theory of structural holes would suggest that what you really want to have is you want to have friends who are not tied to one another, because that maximizes the chances of getting non-redundant information that will then pull you into the group. So 3 friends who are all tied with each other is sort of really just 1 friend, because they're going to all know what everybody else knows, and so you just get the same story 3 times. Whereas if they're not tied to each other, it increases the probability that you get a different story from each one, and hence you get that crucial piece of information that you need to pull you in. So, if the fundamental mechanism of joining is information-driven, then we would expect to see triads would have a depressing effect on the probability of joining. But on the other hand, if joining a community is not so much about information, but about acting on information, that is, changing one's behavior, then what you need is social reinforcement. And now the ties among your neighbors helps to provide that social reinforcement, that density of peer influence that pulls you in. And indeed, that's what they found. They found that the triads have a positive effect. And what that suggests then is that the mechanism of social influence operating here is not just exposure to information, but social reinforcement to act on it. And that is the basic distinction that I've been exploring with a graduate student at Cornell, looking at threshold effects and how different network structures are conducive to the spread of contagions at different threshold levels. And this project is driven by this distinction between the spread of information and the spread of behavioral changes which require social reinforcement. A good example would be an urban legend. So an urban legend, for example, that Einstein flunked algebra, which, by the way, for those of you who went to MIT, it's not true, although many people believe it. And why do they believe it? Well, they didn't believe it the first time they heard it. The first time they heard it, they said, that's ridiculous. Einstein obviously didn't flunk algebra. But after you've heard it 4 or 5 times from different people who presumably don't even know each other, you begin to realize that everybody knows this, it must be true. It's kind of like Wikipedia. So the idea is that as you get the social reinforcement, then now you become yet another voice in the chorus for somebody else. And what we found is that as the threshold for adoption and propagation of a contagion goes above the theoretical lower limit for the spread of a contagion through social contact, which, by the way, is 1, right? The theoretical lower limit is 1. Can't go below that or it doesn't spread through social contact. For any threshold above 1, the network properties that are conducive to the spread of a contagion flip over in the following way. That shortcuts across a network that allow information to go leaping from one area of a network to another area that would otherwise be socially distant. Those bridges, those contractions that allow information to spread really rapidly actually inhibit the spread of complex contagions where the threshold is greater than 1. That is to say, contagions that require social reinforcement in order to get people to change their behavior, to believe in something that's difficult to believe or which violates social norms, and to therefore then spread it to others. And we're looking for ways to test this idea using web data along the lines of what you just saw with the live journal study. So here's what we found using computational experiments on different network structures. This is just a replication of the classic small world study, and it shows that if you take a regular network, a grid-like network, and you tweak it just a bit, randomize it just a bit, then contagions with a threshold of 1 do indeed spread faster with a few random ties. And you see that in this blow up right here, where basically a very small number of random ties will allow information to spread just about as fast as it would on a perfectly random network. And that's the fundamental insight of the small worlds literature. So then we just replicated that. That's all for thresholds at the theoretical lower limit of 1. Now let's raise the threshold just 1 notch to 2 and repeat the experiment. And this time what we find is that when the threshold is at 2, that the rate of propagation drops in this area where we've increased the number of random ties. That is, it takes more time steps to reach a certain saturation level of the network. And when we blow the thing up, we discover something really quite remarkable, which is that so previous work on small worlds claimed that a small number of random ties can approach the propagation rates of a random graph. What we show is that when you raise the threshold of activation even just a little bit above 1, that is, to 2, you got to hear a second person. It's like a newspaper. Got to have my second source, then I'll believe it. Not a third or a fourth or a fifth, just a second. When we raise it to that next step up, the small world actually outperforms the random graph. That is to say, it will spread faster on a small world network than a random network, which was.
Why is that? I mean, that's fascinating.
Uh-huh. It's because the randomization inhibits the spread of these complex contagions because it disrupts the local structure of the network. And that local structure is key to propagation. Why? Because the local structure has overlapping clusters that provide bridges between two clusters. So if your cluster and my cluster have 3 people in common, and your cluster is completely saturated with the contagion, then then some of the people in my cluster are going to hear it from 3 people. All they needed was from 2. I did it with 3. I could do it with 2. They're going to hear it from 2 people, and now it's going to spread to some of their neighbors, and then it's going to fill my cluster. If we perturb this network structure and disrupt that local structure, we disrupt those bridges of overlapping regions between clusters, the thing can't spread. And what have we gained? We've gained a random tie clear across the network, which is in fact useless because they're just going to hear it from 1 person. So we gained nothing, and we lost the local structure that you need for these things to spread. And so what this suggests then is that the networks that are ideal for changing behavior are different from the networks that are ideal for spreading information. So if you're in the behavior change, so suppose you're working in public health. The first thing you want to do is you want to worry about how the disease spreads. So there's certain networks that the disease will spread really well on. Second, you want to know how to get information out to people. There's certain networks that will work really well for getting information out. But what you really want to do is not study how the disease spreads and not study about not just get information out. You want people to change their behavior. You want them to use safe sex practices or birth control or not drink water, so on and so forth. And to get their behavior to change, that's a different network structure than the first step.
You wanted to get, so if it were 2020, you wanted to get Republicans, Catholics to switch from Democrats to Republicans, you'd go through local churches rather
Yes.
than mass media.
There you go.
So
Or the internet.
Carl Rove figured it out.
He may have, indeed. And what we want to do is test these ideas using network data. And trying to test something like this with conventional methods, I just don't know how to do it. I mean, it's not going to be that easy to do it with the internet data, but you can see from the paper that Kleinberg, Huttenlocher, and their students did that you can get some traction. And that's just a first cut on this approach. So the promise is there for tackling some really tough but extraordinarily important questions, because there really aren't many things more important than understanding how things spread in populations. Show me something bigger. That's a big one for social scientists, and it's remarkable how little we really understand those processes. But the reason is that we just haven't had the data and we haven't had the models. And we're now right at the cusp of being able to have the data, have the models, and therefore to see some really amazing leaps forward in the ability of social scientists and information scientists to solve fundamental problems. So there are a number of how am I doing on time here? I should try to wrap this up pretty quickly here. Let me just really quickly run through some research topics that we're interested in working on. We're interested in self-organizing communities, and indeed Microsoft Research is collaborating with Cornell to run a workshop at Cornell in the spring of '07 on the topic self-organizing online communities. And these are really a remarkable opportunity to study social life in a fundamentally important way, to see how communities form. I mean, we just really don't have data on this. We don't know much about those dynamics. We have lots of theories about how people form communities from the top down. We don't know how they self-organize. We don't know how norms emerge and get established, except in ways that are riddled with confirmation bias, these descriptive accounts that that have very little causal validity. And so the study of self-organization is indeed, I think, a fundamentally important area. And not just knowing how it happens, but knowing the consequences of it. In what settings does self-organization outperform socially engineered communities? And in what ways does it underperform? Studying the spread of opinion and belief, a remarkably important area where some early studies are indeed very promising. And we're going to be working on this. One of my graduate students, Tom Lento, who was just at Microsoft Research, is going to be working on this. And the idea is to see how to map the network structures of opinion polarization. Now, a lot of this work is really going to require the development of much better tools for natural language processing. But these are being developed at Cornell. Lillian Lee and her group have been working on movie reviews, and they've developed tools that are very good at giving thumbs up and thumbs down correctly on movies, and they're now moving to do the same thing for political text. And you can do this by training the machine using text from known sources. So if you know the person who wrote it, you know that they're coming from the left or the right, and then you can train the machine to pick text of unknown sources and code it left or right. So one of the really nice early studies was by Adamek and Glantz of the community structure of blogs. And what they found is a very nice result, that they found that conservative blogs tend to have higher density. They tend to link to one another, while the left-wing blogs, the blues, have more outreach. Their network structures tend to be a lower density. And this study was extended by a group in Australia, Robert Ackland's group, to political parties in Australia, to environmental groups, and to reproductive rights groups. And again and again and again, they found the same pattern, that the right wing tends to have higher density ties than the left. So there's something going on here that is going to be, I think, turn out to be a really promising area for people to continue to work. And we're looking forward to doing that with the data we're collecting from the Internet Archive. Then there's the Cornell Archive, which is a much smaller scale archive, which is very useful for kind of scaling up to the web scale. It's smaller and more manageable. And Kleinberg's group studied the change over time in the archive, and they found that the density of this network was not constant, which was what the prevailing view in network theory would lead one to expect. And moreover, that the diameter of the network was decreasing as the network grew. So I will conclude now, and I would like to just leave you with one idea. And actually, this idea, I think, is the one I really hope you remember and think about more than any of the things that I've told you about the Internet Archive and the research that we're doing. Because what we're doing has a hidden agenda. And the hidden agenda, I think, has more important long-term consequences. It's an agenda for social science. And it involves the development of computational social science through collaborations among social, computer, and information scientists. And the inspiration behind this comes from physics. So what was the greatest physics department in the world in the 1960s? We all know the answer. It was Bell Labs, which gave us the transistor, the cell phone, the fax machine, the Big Bang, you name it. They came up with... the
That
big
explains a lot.
Yeah, there you go. So Bell Labs at the Murray Hill, New Jersey facility, a great collection of physicists, actually also economists at one time. And one of their great accomplishments, here it is, the very first working transistor from Bell Labs. And indeed, many people thought that they figured out the transistor by deconstructing the Roswell spacecraft. That's one of the theories. They dismantled it and reverse engineered it, and that's how those things work. But actually, of course, that's not how they discovered it. It was through basic research, which they celebrated. Not applied research, not product development, but basic research. And that's what made that the greatest physics department in the world for many, many years. And so what I think we're now looking at is not just web data. What we're looking at is, I think there's going to be a Bell Labs of social science. It's going to happen. We're ready for it. And it's not just going to be social scientists. It's going to be people coming from physics who want to look at really badly behaved phenomena. They figured out electrons. Now they want to work on the really tough stuff, like people. And it's going to involve applied mathematicians and graph theorists. It's going to involve computer scientists, information scientists. It's going to involve game theorists and network theorists. And what's going to happen is that the very best of these people are going to find each other in a center. Maybe it'll be called the Center for the New Science of Networks, who knows? But it's going to happen. They're going to come together. They're going to produce these collaborations, and there's going to be some really exciting social science that's going to come out of that, and network science that's going to come out of it. And what we're looking for at Cornell, and what we're pushing hard for at Cornell, is a partnership between Cornell and the National Science Foundation. And what we're looking around for is a Ma Bell-scale high-tech corporation with a strong commitment to basic science. So if anybody knows of any, please let me know, and I'll end on that.
With that, let's all do this.